Okay, so what I wanted to get into today. All right, your exam one stuff. So this stuff is basically going to be concentrations, kinetics, and a bit back onto arrow pushing, simply because I know that it was covered kind of in exam two, and also it was in the review for exam three. So I'm just going to get it all out of the wash now, and then focus more on ice tables in tomorrow's video, acid and base equilibria, etc. in that the second exam review video, aka exam two, and then exam three will be more equilibria in general. But enough about what's going to be there. This is what we're doing for today. All right. So from way back when, I know that you guys remember the lovely and wonderful molarity, molality, parts per million, parts per billion, mole fractions, mass percent. That's a lot of different conversions, and I do not have the time to go through all of them. And therefore, I'm just going to ask that you do go through them, or at least have those turbo up when you are looking at them, and put them in your notes for when you are taking said exam. And note that molarity and molality are completely different things. So please, 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 if it asks for molarity, remember that is moles of a solute over the liters of the solution. And when it gives you a molarity, so say it says 0.05 molarity, it is saying 0.05 moles of solute in 1 liter of solution. That's what a stated molarity is. If you're finding the molarity and it tells you a volume, then you have to convert the volume into liters and do the moles that you get from, say, the molar mass or something, and then divide it by the given volume to get the molarity. But if it gives you a molarity, then it's already telling you how much it is in 1 liter of solution. Same thing when it gives you molality. It is telling you that it's in 1 kilogram of solvent. So if it tells you something is 0.15 molality, it's saying it's 0.15 moles of the solute in 1 kilogram of solvent, unless it tells you the mass of the solvent, and then you're solving for molality. So those are two different things, but you do need to know what the stated molality means versus finding molality. The same with molarity and finding the molarity. And of course, the difference between solvent and solution. Solution is solute with solvent. So solution is that in general. So if it tells you I have manganese hydrate, the manganese hydrate together is the solution, but the solvent is the water and the solute is the manganese sulfate. So there is ways to separate them, and you do need to be able to identify them in a question. All right, so let's go through some of these. This is the format that everyone said they liked, so I'm just going to use it and hope that it works for everybody. So when it asks you, okay, what is the mass needed to prepare 25 mils in parts per million? So already we know it's going to be a mass, right? It says so, right? Plain as day. Okay, and it's also giving us a density, and we probably know that the density is going to be what we need to get, again, it's saying mass, to get, because it's in manganese, that solution into an actual readable volume. Cool. So we're going to go with it. All right. Now, when I look at this, I already know that parts per million means that I have so many grams in a million grams of something. And that then, what I do is I like to take off the zeros. I'm like, okay, I want to get this down to about 1,000 grams. Why do I want to get down to 1,000 grams? Because then it's much easier to move between them. So if I take off 3 zeros, I can put a decimal here and divide it by 1,000. It makes it a much more manageable number than a million. A million's a horrible number to work with. I also can note that because it's 1,000 grams, and this is a 1 gram to 1 milliliter, I can already say that 1,000 grams is equal to 1,000 milliliters, right? It's a 1-to-1 ratio. You guys love a 1-to-1 ratio when you're doing C1V1 equals C2V2, because it means you technically can just use it as the equation states. All right, so now I already have this as grams per milliliters, which is great. And I want to find how many grams is needed to prepare 25 milliliters. So then I've just got to set this up as a ratio. I've got grams over 1,000 milliliters equals X grams over 25 milliliters. Now, another way you could have done this. Say you didn't want to do all these conversions. You could have done 550 grams per a million milliliters, but that's just hard to type out in a calculator. It takes too much time. But you still would have gotten this number here, which with 3 sig figs, again, we got 3 sig figs going on, 3 here, etc. You would have gotten 0.0138 grams. All right, how would you prepare 50 mils of solution with 0.005 molarity of NaOH from 0.10 molality of solution of the sodium hydroxide? Again, a very familiar density. Wonderful. Okay, simply going to set this up. What we need to remember is that, again, molality is moles of something in 1 kilogram of solvent. I also need to know that molality is the moles of solute, or molarity is moles of solute in 1 liter of solvent, okay? And then we're going to need to know the molar mass, which you would have to have calculated from a periodic table, or if you're going to be that person that uses Google to look those up, so be it. If that's the way you're going to use Google during an exam, then I think that's perfectly fine because it's not cheating. It's simply looking up a molar mass. So if that's how you're going to use it, then so be it. So I'm going to set it up by setting out basically the molality as is, because I know I'm going from a molarity, or from a molality to a molarity, right? And if I want the molarity, I need to get that to tell me the volume, because it's telling me how would you prepare 50 mils, and it tells me I need to know how many mils of the other solution I need. So how many mils of this 10 molality solution do I need? So I'm going to first try and get this molality into a molarity, and then get that molarity to find out how much volume. All right, so I set this up. Then I realize, okay, this kilogram of solvent, I need to get it to be a solution, because molality is per solvent, but molarity is solution. So that means I'm going to have 1,000 grams of solvent, because 1 kilogram is 1,000 grams. And then I need to add in the solute to get the solvent. And to do that, I need to take the moles that I know it has from the given times its molar mass, and that's going to tell me the grams of solute. And so when I add that together, I get 4,000 grams of solution. And again, I need to make that into liters, because in grams is not what the denominator of molarity is. And to do that, I'm going to need the density. Luckily, again, it's 1-to-1. So all I've got to do is times this by 1 milliliter over 1 gram. And then I've got to divide that by 1,000, because again, it's liters. And that's going to give me a molarity. Perfect. And now I get to use C1V1 equals C2V2, our favorite thing to use when we're doing dilutions. Again, we can use C1V1 equals C2V2 because all of it is sodium hydroxide. If these were different, if these were not both sodium hydroxide, then you would have to find if they're in fact in a 1-to-1 ratio. Otherwise, this would not work. Okay, so I know the molarity that's given to us here, and I know its corresponding volume, and then I know the molarity, and I need to know how much of that. So I'm just going to rearrange this, and it's going to give me 10 milliliters. So it's saying, how would I prepare this? I take 10 milliliters of the 0.10 molality solution, and that would get me the same concentration here. All right, next, how would you prepare 50 mils of a solution that is 0.15 molarity of ammonia from a solid ammonium trihydrate? This is a bit tricky, so it's like, okay, I need to go back and think, what am I going to do to prepare this? Well, I'm going to need grams, because it's saying from solid ammonium trihydrate. Sodium trihydrate is also different from ammonium, but again, I can note that it's a 1-to-1 mole ratio between them. Okay, cool. So first things first, I need to get this molality into moles. So I'm going to take this, multiply it by the volume in liters to get my number of moles. And then I need to get that moles into grams, because remember, this is solid and this is in grams. So I need to know how I'm going to make this into grams. So I'm going to multiply that by its molar mass. This is rounded down because I like simple numbers. If you're doing this at home, or if you're doing it with the periodic table, you'll find it has 0.0183 or something funny. I'm not going through all that. And this is going to give me the grams of ammonia. Cool. Now, how do I get this to relate to this? And that's where I need to make it into a percentage or a ratio. And I like percentage ratios because then it's 100 to a number. So how I'm going to do that? Well, I'm just going to make it a fraction and then times it by 100 to get a percent. So then I take 17 grams per mole. That's the mass of the ammonia, and divide that by the mass of this ammonium trihydrate. And then I note that that's 17 grams, because that's the ammonia, plus 3, because there's 3 moles of water, times 18. That's the molar mass of water. And I times that by 100 to tell me the percent of ammonia to ammonium trihydrate. And that percentage then tells me how they relate to each other. So, again, because they're in a 1-to-1 mole ratio, that's how this works. If they were not, then you would have to do this percentage and then do the mole ratio times this percentage to get the further number. But we're 1-to-1, great. So I'm going to take the mass, multiply it by my percentage, but remember I want this to cancel, right? I want these to cancel because I want to know how much of this ammonium trihydrate I want. And so I want that to be in my numerator so those don't cancel. And then I'm going to get this mass, 0.535 grams of ammonium trihydrate, is how much I need to prepare the 0.15 molar of ammonia. Awesome. Finally, for concentrations, we want to calculate the percent by mass. This is one that we also had a lot of trouble with. Of sulfuric acid in a 1.25 molarity solution, here I go mixing it up, of sulfuric acid in water, and the density of the solution is again 1. Please don't always assume it's 1. I picked ones that used 1 just to keep the math simple, but for your sake, please don't always assume it's 1. Double check that it is 1. All right, and then I posted the weight here of sulfuric acid is 98.079. All right, so first, I want to get this into a gram to gram ratio, right? Because this is percent by mass, kind of what we did up here. However, with a given molarity, we have to go through that molarity. So I first need to get it to grams, and then I'm going to get it to grams of solution. So I kind of did this in one step. First, I did the moles of the solution times its molecular weight, and that gets rid of the moles of sulfuric acid and leaves me with grams of sulfuric acid, right? Because this is the grams of sulfuric acid. Then I also multiplied it by the actual density, but remember 1 liter, and this is 1 liter, would mean 1,000 grams, right? Because this is milliliters, so that's the conversion I did here. So this is really 1,000 milliliters. But 1,000 milliliters is 1 liter. So that's how this cancels out. And now I'm left with 1,000 grams of solution, which is what I wanted, right? I wanted this to be solution in the denominator and the mass of the sulfuric acid. And then remember, solution is not just water. So some people like to backtrack this and also do it multiplied by its molecular weight of water, but that's not what the solution is. So that would take you a step too far. So I get this much of grams of sulfuric acid to grams of solution, multiply that by 100, and I get 12.3% is how much sulfuric acid is in the water. Awesome. Okay. And next. All right, I want you to take a quick breath, jam to a song, snack out, look outside, whatever you got to do, pause the video, go do that. It's very important that you don't get stressed. I feel that this very strongly. I had 12 exams in my final year, and there was basically what they did is we had 5 weeks, 3 weeks in a row, we had 3 exams. All of them were held back to back, same day. You guys have that luxury that you can move them about. We did not. And did that for 3 weeks in a row, and then we had a 4th week break, and then we had a 5th week where we came back and we did 3 more exams. And of course, no one took that fourth week off at all. So I remember getting really stressed and really down on myself, and I'm here to tell you that taking a break does wonders. It makes you come back rejuvenated, fresh, ready to take in more information. Like kinetics, so much fun. Don't forget the units of the different reaction orders. It's so important to remember that when you are looking at a graph, you can be able to identify not only the reaction order, but also you are able to know that the units of that reaction order. Remember that its reaction rate is determined by the slow step. So what is rate determining? The slow step. Think about when you're running a race. The slowest person is who people say is their weakest link or whatever determines your race. This is the truest in kinetics. And then finally, can you do a reaction mechanism? What I mean by that is when you see a bunch of elementary steps together, can you write them together in one cohesive reaction mechanism? And then how comfortable are you solving with first order reactions, half-life equations, etc.? I go through a few of them, but I want to make sure that going through them, these are not the only ones and you do need to revisit them. All right. So this is exactly what I was talking about. Remember, zero order is molarity per second, and you need to know that these are the half-lives that have to do with zero order equations. Same with first order. Half-life is really nice because basically we can find our reaction constant from them. That's always wonderful. Same thing with our second order. Always easy to find the half-life, and also it's easy to find the reaction constant if you are looking for it. So just be sure to remember these are how you find them. And also, I don't show them on here, but know the integrated rate laws. I go through one integrated rate law question, but you should be able to know the integrated rate laws for zero order as well as second order, because I go through a first order one here. All right, so some kinetics. One thing that everyone forgets about kinetics, and this is why I put this in there, and everyone gets flustered, is rate of disappearance and rate of appearance. Because when we think kinetics, like you and I and everybody else, we think 0, first, second, third order, done. Everyone forgets about this average rate of disappearance and all of that jazz. So, especially when we're given an equation like this and we're given the rate of disappearance, and everyone freezes up and they're like, I see no indication of what order this is, and there isn't an indication. So what you're going to remember is that rate is equal to 1 over the coefficient, in this case 1, times the reactant. And it's always negative for reactants, right? Negative for reactants and positive for products. And again, negative 1 over 3, because that's our coefficient of the rate of disappearance of this reactant. And then 1 over 2 is the rate of appearance of this product. Now, look back up here. It's saying this is the average rate of disappearance of Cl2. So I know that I'm going to focus in on Cl2. And I'm also going to note that it's saying what is the rate of appearance of this product. And therefore I know that we could care less about F2, because that's not what we're focusing on. I want to know how these two relate to each other. So then when I look at these two, how am I going to make it so that this is alone, all by itself on this side? And basically all I've got to do is multiply this by 2. Because I want this half gone. And that means that the rate of appearance of this product is going to equal -2. Don't forget the negative. Please don't forget the negative. It's so easy to forget. It's so easy to throw away. Don't forget the negative. -2, because again, 1 is over here, so 1 times 2. The rate of disappearance of this chloride is then, we're just going to plug and chug. Plug in this number right here, and that's going to equal -0.0105. Okay, so please, again, big note, always just simplify it for yourself. Don't leave it in this big chunk and then you get confused later and you're going to plug in the wrong numbers. Just simplify it. Same here. So this is saying decreasing, and we want to know how NO is changing. This is another one that is basically focusing on relating something and keeping track of your coefficients in this case. So I write out my reaction rate as I did above, and I note that now the two they're relating have a very similar denominator. Whoop, I didn't mean to make that square so weird. But I'm still going to do the same thing. I'm going to multiply this by 2. I just note that I have a -1. I don't know why this was the most missed on one exam, but I think it was because people just did -1/2 times 2 and either forgot the negative or put 2 for some reason. Either way, please don't do that. If you have to type everything in a calculator in these exams, sometimes it's worth it. And then I'm going to plug in, just as I did above, my given rate, and then I get this, which again is just the -1.5 times 10 to the -4. Don't always be so suspicious. That was another thing. I noticed a lot of people picked the one that was just above it. And it was funny because in the exam I noticed, in this past exam I was looking at, it was A, and this one was A as well. And I could feel why people would think it's weird, because it's basically the opposite of this. So I can see why that was, one, that was mean, but 2, not mean to the student, but mean of the test writer. But also I can see how it would be mean to you and why you would choose to just pick the other one. So that could have also been why this was most missed. But trust yourself. Trust yourself. Always trust yourself. Can't stress that enough. All right. This was one that you've seen on a partay, and a lot of you had asked me about it, and I just want to remind you because this will be an option. So this is saying that a radioactive isotope is medicinally used as a radiotracer. So if you already know which one I'm talking about, you're going to flip, find that partay. And it's saying that it gives you the half-life. And it's saying if a patient is given 0.45 grams of iodine-131, calculate how long it would take in seconds for 90% of the iodine-131 to decay. What that means is you want to know when the TA of T is, that LNA of T is when there's 10% left. 10% of that 0.545 grams. It's saying would take for 90% to decay, and that just means that 90% is gone. A lot of people then multiply 0.45 grams times 90 because they see a number. That's, I think, where people go wrong on this. It's actually 10%. It's 10% that's left, and that's the only thing that we're going to be able to find the concentration of. I can't find the concentration of what's decayed, but I can find the concentration of what is left after decay. All right? So we use this lovely equation here where t1/2 equals ln of 2 over k to find our k value. Again, we are given the half-life, wonderful, and ln of 2 is simply a plug into our calculator. So now we have our k value, fantastic. And then I'm going to notice that this is a of t, so this is at a of time t, and we're trying to find time t. So then I know that that's going to correspond to the 10% part of the 45 grams. So I know that this is where I'm going to plug in my 10%, equals the k value that I just calculated, t that I'm going to find, plus ln of the initial, which is, again, the patient was given this, so I know that's my initial concentration or mass. And then when I plug all this into my calculator, I get the seconds. Please remember to note seconds because sometimes what they like to do is then say years or days even. So remember your conversions. There's 60 seconds in a minute, there's 60 minutes in an hour, and there's 24 hours in a day. Some people do 60 just because they're on a 60 roll. And finally for number 4, okay, I'm going to note down that with these, all you got to do is find what matches and what doesn't. So when I look at reactions 1 and 2, I note that they have the same reactions for OBR, and so that this then will tell me the concentration of fluorine. Great. Or not the concentration of fluorine, but the reaction order of fluorine, right? So I'm going to line them up as is, and then all you got to do is divide them by each other. So take a big division of this and a big division of this, and these divide out to be 1, so basically they cancel out, right? And when I divide this by this, I get 2, and when I divide this by this, I get 2. And so 2 raised to the power of 1 is going to get me 2, and so therefore I know the concentration of fluorine is a first order reaction. Same over here, divide the, I went up, I didn't mean to. This divided by this is 2, this divided by this is 2, and this divided by this is 1. So we can cross that out. All right, and then I know that X equals 1, and so therefore I know that the concentration of oxygen bromide is a first order reaction. So then I'm going to go over here and, yep, 4 matches with that perfectly. And in case there's a follow-up question that asks you, what is the overall rate order? You're going to say 2, right? 1 plus 1 is 2. Finally, our favorite. We love using the wonderful and always integrated rate law. All right, this one I think people went wrong on because they didn't see how to manipulate this table and were very confused. And that's understandable when you're under a lot of pressure. And so I note here that it gives me time 0. And I know that this is the concentration at time 0. So I already know that I can plug that in here, right? Then I can pick anyone. I like to pick the third one. It feels nice. I don't know why. And then I note that I'm looking for K. Okay? And I then go back up and I note that the time is given to me, so I plug in my time and I plug in that concentration at that time. Plug this all in, do some math, and voila, I've got K. Now, what in the world is going to be the units? Okay, so yes, we could do a quick, okay, well, this is the ln minus the ln, so this is unitless and this is per second. So you're going to be like, well, Victoria, easy peasy, this is per seconds. But how am I going to know it's per seconds? And how did I even know to use the first order rate? Okay, well, first of all, this kind of set me up that it's going to be first order, but why did I do that? That's because it says it only depends on the concentration of NOBR. Whenever it says it only depends on one thing, that's first order. If it said it depends on the concentration of NOBR and something else, second order. If it says it doesn't depend on the concentration, 0 order. All right? So be sure that we read these and note the language because the language tells a lot about what this equation is. Another break, go have a relaxing time. You know, I just miss finals and I don't miss finals. And when I came to Purdue and found out I still had to do finals, I remember dreading it and absolutely hating it. But I do know that one thing I do love about finals is the relief when it's over and when I know that I've done all that I could do for an exam. And that doesn't mean getting an A. I got 40% on my physics final. 40%. And that was pass in physics. And boy, oh boy, was I, I don't want to say it ruined my GPA because I still got a really nice GPA at the end of it all, but it definitely made me have to work for a nice GPA. And I have to say I don't even regret it. I'm just glad that that exam was over and I never had to look at a ball rolling down a plank ever again. All right, arrow pushing. Everybody hates arrow pushing. I don't know why everybody hates arrow pushing. I think it's because it's so organic, it's disgusting. But I know that I really, really want to do arrow pushing only once when I'm showing you guys. And the reason for that being is that it shows up so much, but I want to put it all concentrated to one video. The thing that we always want to note, though, is it's about electrons. Here's something that's very electronegative, especially because it's got this minus sign on it. So it's going to want to attack something very positive. And this is very positive. It's got this electronegative group pulling electrons away from it. It's got two hydrogens. Those aren't really helping. And it's got this ring, and rings pull electron density towards them because this ring is constantly flipping around. So this is pulling electron density. This is pulling electron density. Hydrogens aren't giving much electrons because remember they have one. So this is very positive. Now somebody asked me, why isn't it going to take a hydrogen? Well, then that leaves this carbon very exposed and unhappy. Carbons like to have 4 bonds. And even though this hydrogen will be happy, the rest of this complex, not so happy. And so you want to make sure that what you're leaving behind is just as happy as what you had to start. Well, somewhat. It should be actually more happy. And in this case, this is a 4-bound carbon, very happy, and a Cl-. Again, so electronegative, it's happy as is. And this technically has all 8 electrons. Happier. Fantastic. Plus an extra 2. And then the other thing I want to ask is how comfortable are you looking at something like this? So when it asks you, this is again on part A, and that's because they all kind of come up, is reading language. So it says how the electrons arrange in the reaction of a hydroxyl radical to produce water and a methyl radical. So if it's something that's producing water, well, water is H2O. And I know that that means that whatever is happening better give me 2 H's and an O. So all of these seem to be doing that. This oxygen is getting a hydrogen. Cool. This oxygen's getting a hydrogen, this oxygen's getting a hydrogen, this oxygen's getting a hydrogen, this one's getting a hydrogen. So that gave me no clues. But then the other thing is this says radical. Radical means that we're looking at half arrows. Half arrows are the ones that only move 1 electron, and a radical is something that has 1 electron. And so that crosses off A, B, and C, because they all have full-headed arrows. Thank goodness. Now we're narrowing it down to 2. All right. Now, the problem with this one is I've got this methyl radical forming. That's good. I've got 1 electron on the methyl group. That's what I wanted. And I have this arrow pointing into a bond here. But remember, a bond needs 2 electrons. And that means I need to see 2 half-headed arrows going into the same direction. Otherwise, what's happening is this hydrogen is half bonded to this oxygen, and this oxygen has a radical on it. That really what's going to happen is if this reaction went forward, it would then do this. And it would form the actual full bond with the hydrogen. So this is very wrong because, again, a bond needs 2 electrons. And I now see 2 electrons forming a bond here. And that's what we want. So that is why E is the correct answer. All right. Get me going. Ooh. There we go. All right. This one. When I'm looking at this one, it says using arrow pushing, how many electrons are arranged in the first step of this reaction. So the first thing I'm going to note is that we are looking for something that is going to make a carbocation and then leave behind bromine. So first of all, it's deciding who's going to take the electrons and who's going to give them. So if I move electrons this way and then move electrons here, but then that means I'm moving a double bond here and a bond here. And that's not what this represents. So I'm going to cross that through. All right, let's see. This one, I'm making the hydrogen form here, and then this pops off. But then I'm left with a double bond on this carbon. And that's not what I see here. So I'm going to cross through E. This one, I have this forming with hydrogen, but then I have bromine forming the bond with hydrogen. And that's not what's happening here. Because I'm not having bromine bond with hydrogen plus the carbon bonding with hydrogen. Hydrogen can't bond that way. It can only bond once. So that H is gone. Okay, this one shows that hydrogen and bromine break their bond to attack this carbon. And then this double bond breaks here. And then puts a negative charge on this carbon. But we want a positive charge. And if I want a positive charge on carbon, I want electrons moving away from carbon. And then if I want a negative charge on bromine, I need electrons moving to bromine. And that's exactly what, with no letter, C is doing. is that you've got electrons moving away from C, leaving a positive charge on C, and I've got electrons going towards bromine, which is giving a negative charge on bromine. And that's what I want to see. So C is correct. All right, and this one, I wanted to kind of draw through this one because this one kind of embodies what we just showed, except it's a two-step program here. So again, these are very happy. Dichloride has a good equal share here, right? Very planar, very happy. But what's going to happen is this electrodensity, lost my pen, is going to form a bond with this chlorine, and the electrons are going to move onto chlorine's twin. It could have tacked either side. So then what you're going to get is you've got now single bonded carbons, and that carbon is also bonded to the Cl. But remember that the electrons, and I'm sorry I flipped this just because I want to show it attacking much easier. But because those electrons moved away from carbon, that leaves a positive charge on carbon. That's something to always note when you are moving electrons in general, is the charge that is left on what you took away. So again, because I took away electrons from carbon, it's going to have a positive charge on it. But remember that chlorine, well, that means electrons had to move towards chlorine. And because those electrons move towards chlorine, chlorine's now going to have a negative charge. But if you have a negative and a positive that are next to each other, you best believe that that negative is going to want to form a bond with whatever is positively charged. And if that happens, then you're going to get this product. So just be sure you're noting what is actually getting the electrons and who's losing the electrons. Okay, that's all I have for you guys, and I hope to see you tomorrow for exam 2. Review, not the actual exam. Bye.